Can you hear me okay?
Yes.
Yeah, okay to me.
Problem solved?
Problem, yes. Problems fixed.
Right.
Okay, yeah. You hear me?
Yes, yes.
I can hear you. Okay. Wonderful.
You can share your screen when you're ready.
Yes, just a moment. Okay. You see?
So this was running, you checked it's working.
Yes.
Yeah.
This is my first block.
Okay.
The output is the orbit, so the 3 components of the position and the 2 components of the velocity. And now we have to create the desired quaternion.
Yes.
So I create a MATLAB function, and okay, I want to try in this way to first create the DCM, and with the LVLH axis, R1, R2, R3, and then convert DCM to quaternion. Or I remember that you yesterday converted the DCM inside the MATLAB function. So yes. I think copying the code inside the block, the Simulink block.
Yes.
Okay. Can I try to export to output DCM and then convert in Simulink with the block? I don't know, because I have this idea. Okay, so the output are the DCM, the home desk, that is the omega, the desired omega, and of course 1, 2, 3. And we can then DCM. And the inputs are, of course, H and orb. Okay. I write first the equation and then I convert the inputs. It's better. Okay. The equation are if we want.
Excuse me. Am I the only one who is just seeing Simulink and not your MATLAB code?
Oh, yes. Oh, you're working in MATLAB. No? We're not seeing that.
Okay, sorry. Probably I just shared only one window. So how can I share all the windows? You still see only the Simulink.
Yes.
Green one. Now? Now?
Okay, now we see anything.
Okay.
Thank you.
Okay, welcome. No problem. Okay. What I'm doing? The A3 that that's pointing to the Earth, towards the Earth. So is what I call orb, the position, of course, or divide to the norm. Orb 1, 2, 3. Okay, and two is the H vector, parallel to H vector, and R1 define so cross Quaternion. Okay, the DCM is 1, 2, 3. And on this is no, okay. divided to norm or 1, 3. Squares. I don't remember.
Yes, the square.
Squares, okay.
Not everything. Only the denominator. Yes.
Is it okay?
Yeah, I think so.
But this, okay.
Hold on a second. I'm not sure the parentheses are in the right place. Are they?
These parentheses to with
No,
for
so no, I think I'm confused. I think you need a parenthesis before the square and remove it from where you are with the cursor right now.
these.
Because you're doing norm and then you square it. Instead here you're doing the norm of the square of the vector, which is not gonna work. Yeah. And so you need another parenthesis. Yeah. Yes.
Correct.
I think so.
Okay. So we had DCM. DCM. Okay. I come back to Simulink. So we have H and norm. H is the crossover R0 V0, but R0 V0 are defined into the initialized in your initialized file.
It's actually it's actually right there. So you actually have H.
Okay.
So if you run these,
you
can use it, yeah.
Constants and yes, okay. While orbits come from here. Okay, but I'm not sure that because okay, 1, 2, or 3 simply go to sim out. 1. Okay. Same for on this.
Yeah, these quantities is, I mean, you can plot them, but you're not going to be able to see much. I mean, the vectors and a matrix. Yeah.
Okay, now there is the problem of DCM that
Did you try to run this? You want to try to run it to see if it crashes?
Yeah.
Yeah.
Just for
Sure.
okay.
Yeah.
Incredible, but it seems it works. It's working.
So can you step a second back to the computation of this DCM?
Yes.
Okay. Okay, thank you. So it's the square of the fraction of the norms times the second component of A.
Yes.
Minus the second.
Correct. Okay. Minus.
Okay, thank you.
No problem. Professor, I plot something, or I move to DCM. DCM.
I would move on. I mean, if you plot these quantities, you're not going to be able to really judge whether they make much sense.
Okay.
Yeah.
Okay. So within the aerospace block is link that is called DCM to Quaternion. DCM to Quaternion.
Also, you do have the aerospace toolbox?
Yeah.
Nice.
Maybe I have to use something else because someone doesn't done. Okay.
Well,
DCM to Quaternion, but okay.
the only thing is, if you go inside, you need to. Can you double click on the block?
Yeah. Intolerance.
Okay, so determine 4x1 quaternion orientation vector from a 3x3 direction to some matrix. Yeah, as I recall, this function has the scalar component of the quaternion as the first element, but all the equations that I gave you actually work with the quaternion with the scalar component as the last element, just to keep in mind. Remember that I did that.
So we have to rearrange them.
Yeah. But yeah, that's fine.
So if I well understood, the output is that the scalar components is the first component. In the okay.
And if you want to use the equations I gave you in the slides, though, those are for the scalar at the last component. That's it. But yeah.
Okay.
So yeah, in principle, this does everything for you. So it's not like you need much more. But for the ones who do not have this toolbox, remember that I posted a function. Let me share my screen real quick. So this is the function that we showed yesterday. It takes same variables and puts together a 3, 2, 1 DCM. And then I copy pasted the function I shared with you, but it's a little modified from the MATLAB one, because if you look at this, the MATLAB one has this, it can do it for multiple matrices at the same time. So I removed the for loop, and the indexes, everywhere they appear, these i's, I remove them so that it does it for just one. Compare the two, for example, here is Q4 equals 0. In the original one is QI4 equals 0. And here there is an additional I. In my case, I don't have it. This is the trace of the DCM. Let's see. All these other instructions, for example, the I's are all gone. So it just needs a little bit of adaptation because in this version we're doing it for one DCM only. But I guess there are other ways to modify this, or just use it as it is. Yeah, I haven't tried to just use this as it is. I just copied basically everything that is from the second to last end to here without the 4, and I removed the i's. That's what I've done. If you want to, if you need to use this, but anyways.
Okay.
And then the couple things. So you've done this, the omega. Okay, you have it. The two things that you will have to do, I guess now.
Yeah.
Are rearranging the quaternion, and also, you know, I wish I remembered why I ended up doing this, checking the dot product between the old quaternion and the new one. But I think I had a case when I was testing the software where it would spit out, you know, between time steps, two very different quaternions that they did correspond to the same orientation, but they were just jumping basically in terms of continuity, and so this helped with that issue. So those are the two things that I recommend you do in your software now. I'm gonna give you the screen back.
Okay. So I don't know if I create another function.
Can you share your screen again?
Ah, see, yes, sorry.
That's fine.
Let's call Q this and plus take Q.
And I suggest that you also input the previous Q. So basically two inputs actually.
Q just old.
The one, yeah, Q old or something.
Q.
Yeah.
Q old and Q.
Sure.
Okay, that's so Q this is the rearranging of the input. So
Yes.
okay, so that the first component is the four components of the Q vector.
And 1, 2, 3.
Okay, and then the if the dot product of QDES and QDES sold is minus and 0. Dot QDES is equal to minus QDES. Correct?
Yes. Don't forget the semicolon, otherwise it will keep printing stuff.
Sorry?
At the end of the instruction inside the if, a semicolon at the end.
Yeah, yeah.
Yeah. So yeah, outside.
The memory.
Why is it not showing two inputs? Oh, now it does. Okay. Okay.
So this is world, QDS, and memory.
Mm-hmm. Yeah, you can flip the blocks, you know.
Ah, yeah.
Okay.
Okay. Yes. Let me check if works. Okay.
Line 3, column 9. What? Oh.
Y Q.
I think I had an instruction that initializes the Q desired something, because yeah, I don't know why. I think I was having the same problem.
Yeah. The problem is that wait. Yeah. Initial conditions.
Okay. That could be the problem.
Let's see now. No. Could have solved on the problem. Yeah, Q hold. Okay. Hold. Okay. Let me check. Hold is this. Okay. Could has memory insert. Okay. No. Okay.
Okay.
And then the last thing, the conversion from inertial to body, right?
Yes. So what I suggest is you take what you've already done, assuming you've completed homework 1, the block that simulates the dynamics and the quaternions, and you take that quaternion to put together the rotation matrix to apply to omega. Make sense?
Sorry, no, I didn't understand. Sorry.
So what we're going to do now is the Q desired is the desired quaternion of the spacecraft in the inertial reference frame, and that's okay. So you don't need to modify that. But the omega, the way it's expressed now, the omega desired, is expressed in a basis that is in ECI, is not the basis of the spacecraft. So you need to rotate that vector, project it into the spacecraft axis. And to do so, you need a DCM that goes from inertia
to body.
Spacecraft. And to assemble that DCM, you need the quaternion, for example, of the spacecraft.
Okay.
So it will be the homework 1 was doing that. It was simulating the dynamics and kinetics, the kinetics and kinematics, so that you have, for example, the quaternion history. So you can grab those blocks and put them in here, so that you have somewhere else you have a queue that is being generated, and you can put together the DCM.
Yeah, okay.
The queue of the spacecraft.
To be honest, I didn't finish homework 1. That's I missed the last block. So
Well, it looks like you have So the last
Yeah.
one, the comparison. Oh, you have to do the Quaternion. Okay, let's finish it.
I have to the normalization, right? That the last thing to do is to normalize. And then to... No, I think that is for the Quaternion side is
That's it.
That's it. Okay. These we go. Oh, problem is this problem. Okay.
So, assuming that everything is working fine here,
Yeah.
basically in the other model, you only need the top and bottom. You don't need this or angle part in between. So you can copy everything.
Yeah.
And paste it, but then you can also remove the other angle stuff.
Yeah. Okay. Just wait to end the simulation.
Oh, it's running. Okay.
Okay. Probably I can. In the meantime, I can create, I don't know, a subsystem. Makes sense.
Yeah.
So, why it doesn't do? Okay. Okay, it's quite slowed down from the other simulation. So okay, so if I copy all these blocks in the subsystem, okay, these works. Okay, so I place all the block in subsystem where the inputs are Q. So just a moment. So to have a clear view, okay. Then from homework 1, I copy these blocks.
Yes.
I create another subsystem. Okay, and these blocks.
Yeah, you're gonna erase them.
I don't need. Okay, now this must be an output. We need the body quaternion, so this is our QB. Okay. So this is the body quaternion. I don't like the content preview. So okay, so here we need as input. So, oh, sorry. The Q, that's the QB.
Mhm.
Now,
You probably have a block in the aerospace toolbox that does Quaternion to DCM as well, right?
yeah, just a
Oh,
moment because
yeah, it's dangerous.
started the print.
Dangerous because now our Quaternion is yeah. I don't know if I'll use it. Because you need to put together the DCM.
Okay, now what I have to do is to create the DCM to convert inertia to body, correct?
Yes. Yes.
Okay, so we have the Quaternion, and then we can convert the Quaternion to direction cosine matrix.
Yes. Yeah, I'm just afraid that this is going to expect the Quaternion, with the scalar at the first component. So if that's the case, you need to rearrange, before you give it.
In the original form.
Yes.
Yes.
Yeah. So the scalar is definitely the first one for MATLAB at least. Yeah, I'm sorry that I gave you everything the other way around, but I was used to that.
Okay, I can use your function or with the original form of the Quaternion. So I have to.
I can put it in the chat. It's this function here.
Yeah.
Here you go.
Okay.
That's what I'm using. I lost. Oh, okay. Okay.
The function.
Yeah.
In the top.
No, I put it in the chat actually. If you copy the text from the chat, it should be there.
I can see.
You cannot? Because
No.
I didn't send it. That's why.
We don't use it.
Sorry. Now it's here.
Okay. Okay.
So yeah, this expression is the same one we see in the slides.
Okay. Here. Create MATLAB function that is the same. So, okay, inertia as a body, Q, DCM. Okay. So the input is
Okay.
This is the DCM, and so the output of this must multiply matrix the omega desired. Okay, and this.
Sorry, this function gave us it's called the inertia to body, but actually it's just a quaternion to DCM, or is it specific for inertia to body?
No, yeah, I called it that way, but yeah, you're right. It's Quaternion, yeah. I named it that way to, I guess, to remember what I was doing. Yeah, you're right. You can just call it Quaternion to DCM.
Okay, so this will be output of that subsystem. That is
So this is the final omega desired that you can eventually use. This in the body axis. And then other outputs of these blocks should be the Q desired of this subsystem, the Q desired. Hey guys, can you mute your mics unless you're talking?
Sorry.
That's fine.
Q desire
and then the last one that I had, and this, we will see why when we talk about the feedback control that I'm suggesting you to implement, is the time derivative of omega desired. So I have a numerical derivation of omega desired. There's a block. Yeah.
This one.
Yeah.
Okay. So we output both on this B and also the derivative.
Mm-hmm.
How can I say? I can name that. No.
Omega desired dot. Okay.
That's dot. Okay.
All right.
Okay.
So perfect.
Okay.
So this, aside from tweaking and cleaning it up, it's now allowing you to create on a given orbit the desired quaternion and angular velocity to track LVLH. So those three outputs will be useful as a reference trajectory in terms of orientation for control purposes. The few things that you may want to do is stop time is T final, and you want to call the initialize in the init functions. You want again,
The initializers are.
I think it's called initialize. If you just grab the one that I gave you. Yeah, I don't know if it works with the dot M. It definitely does without. So
Okay.
Yeah.
Yes. And okay.
Apply.
The
And then I think you had some number for the final time. You can just call it TF because it's part of the initialize. So at least it will run for an orbit.
TF here.
Mm-hmm.
Okay.
Okay.
We this big.
Let me see. I'm not plotting the omega desired, but if you want, what I can do is look at my model and put a scope there and just compare as if they are the same, just for fun.
Okay.
So yeah, the omega desired, for example. Okay, I'm gonna run mine.
I have to stop the sharing?
No. I was suggesting just as a sanity check, since you should have the same initialize and the same everything, pretty much. Maybe not. They should behave the same way. The only thing is, if you go inside the first subsystem, body Quaternion.
Yeah.
Oh yeah, I can't really compare because mine is the closed loop anyways. The J now that you have the initialize, you can actually use the one in the initialize. I don't know what it's called. I don't remember.
Yeah.
Yeah. So that we have the same.
Is one.
Yeah, just J. Yeah.
Yeah.
So call it J. Oh, you can just type J in there in the block.
Yeah.
And then the initial conditions as well. You want to make sure that they are coming from the initialize.
That's so the omega 0. That is.
Yeah. So we're working with the same setup, you know.
Yeah. On 0. Okay. This is 0, 0, 0.
Well, it will eventually be an actual torque that will be coming from the momentum exchange devices. So, what was I going to say?
I can see
the reality is that we'll change the block of the dynamics entirely because we'll have the momentum exchange device. It will be a lot more complicated. So for now, yeah, just leave 0, 0, 0 and 0 and everything else. But we'll probably throw away eventually the first block here because it will not be just a rigid body.
Yeah.
Without anything inside. It will be a rigid body moving things inside.
Okay.
And that's
001.
I don't know what it's called.
Is a good 0. Okay.
Wonderful. Does anyone have any questions?
Okay.
You following what was going on? Is this useful? I'm sure.
Yes, it was.
Sure, it's useful for those who are not very familiar with Simulink. So, okay. Yeah, well,
just to recap what we have developed till now. So we have a block that computes, that integrate the omegas and the torque and get the orientation of the spacecraft. So it gets the torque and it put out the Quaternion body that is the orientation of the spacecraft, right?
Correct.
Then we have another block that solves the orbit, so compute the position and the velocity of the spacecraft, and then another block that gets the position of the spacecraft along the orbit and use it to compute the desired orientation and also the desired velocity.
Correct.
Right.
Yes.
Okay. So we will then put in something that closes the feedback between the desired omega and the torque.
Correct.
Okay.
Yes, and as I just said, the Euler's equations block will be replaced by something quite complicated, more complicated, because we will have generally variable speed control moment jars. We'll have rotating wheels that we can control in RPM and control also the gimbal angle. So we'll close the loop on the gimbal angles as the actuation variables and also the RPM of the of the wheels.
Okay. But we may also keep the same block and just add the block before to compute the torque, right? More or less.
Well, yes.
We can say that that is our process, and then we have to put the actuators in front.
Yes. I would rather do it a little different just because, well, I mean, yeah, it's a way.
Yeah, but I'm talking about just about the concept to be sure I got the framework where we are going to build.
But the reality is that the dynamics of the system, spacecraft plus the actuators, you know, even for example, the inertia matrix of the entire the entire system, spacecraft plus actuators, is not just J anymore. It's J plus the contributions of all those systems, the variable speed control moment gyros with the rotation matrices involved. So, I'll do the derivation of the equations, and I think it's preferable to have a new block. The principle is the same, that, you know, it takes in the torques, the commanded actuators, positions and rates, and it generates as output the angular acceleration of the spacecraft, exactly like it's happening now in the Euler's equations block, which is very simple. It will become a little more elaborate because there's
because in this case the actuators are embedded in the process, so it's not that easy to decouple the two systems.
Yeah.
Okay.
The actuators are part of the dynamics.
Okay. Yeah, I see.
Yeah. Okay, any last minute questions this afternoon? What I will do is continue on the environmental torques, because we started on that topic, and I think they're important to know, because the way I see it is part of the dynamics, really. Even though we use them as torques, as control torques sometimes, you need to know that that's the environment you're flying through anyways. So it will take a while to finish that, but tomorrow I'll definitely want to start on deriving the equations that you do have in the notes, by the way. Everything that I'm deriving is in the notes. You have my handwritten notes. I will start deriving the equations for the dynamics with variable speed control moment gyros, so that we can attack the rest of the homework too, sooner rather than later. Again, my goal is that you really are in good shape, almost everything done by Wednesday, so you're gonna have to think about it after. But you know, we'll see. You can finish after Wednesday, but I would like to, you know, put you in a situation where you don't need much more after that. Make sense?
Yeah, sure.
Yes. Questions? Was this what some of you were hoping for this morning? So?
Yeah, it was very
Yes.
helpful.
Okay. Well, we'll see you in what, 3 hours? Let me see. Yeah, 1, 2, 3 hours.
Sorry, so are we having lessons also the next week?
Yeah, I have Monday through Wednesday, yes.
Oh, okay.
1 hour Monday.
Okay, I don't see it on the schedule.
What?
No? Or
Yes, there is. It's because there's only from Monday to Friday, but it goes also to the 31, I think. Their schedule.
31st
okay, I'll find it out.
So it's the same for schedule also from Monday to Wednesday of next week.
Yes, correct.
Oh, okay, I see. Okay.
You see it?
Yeah.
I thought I put it on the calendar. Yep. So, and it will be mostly, you know, working to finish the homework, I hope. But also, if we have time, I'll keep working on other concepts that are absolutely important for spacecraft control. Sounds good?
Yes.
As
Yes.
always,
Yes.
let me know if everything is going okay, if the pace is right, if it's too many topics or not enough. But I think we're keeping a good pace. All right, see you in a bit. Bye.
See you later.
See you later.
Thank you.
Bye.
Bye.
Bye.